Last time in the lecture, we had gone over the following items of this segment, and that is to say, linear time invariant systems. We had, of course, done the introduction. We had looked into what linearity was. We had looked into what time invariance was. Then, importantly, we had gone through several examples of linearity, time invariance, etc. And most importantly, we had come to the centerpiece of this segment, which is that there is something called an impulse response for linear time invariant systems, and that impulse response, once you know it, you know pretty much everything about the system. So today what we are going to do in this brief segment is I'm going to give you an illustration of the convolution expression that we came up with in number 5 here, both in terms of equations and in terms of pictures. And finally, I will give you a short summary of similar results in the continuous time domain. Of course, everything we have been doing over here in terms of derivations and so on has been for discrete time because it's a bit easier. So now, see. So let's try an example. It's more than just an example in this case. It's a generic example of a discrete time state space system. So x of t plus 1 equals, we'll keep it all scalar, a small a x of t plus small b u of t. This is the standard state space system we have seen, together with an output equation y of t equals c times x of t plus d times u of t. And importantly, we will set initial conditions x of 0 equals 0. Now, the issue of initial conditions, and in particular non-zero initial conditions, is quite a tricky one, and there will be quite a lot of discussion of this going on during your discussion sections, and so I'll leave you to look it up over there, and also to try to work it out yourself. That really is the best way of doing it. But here we will take x of 0 equals 0, and our convolution equation. Let me derive it. So we will assume that that the system has an impulse input, because we want to find the impulse response. So we are going to go about this very, very slowly. We will start with y is 0. Y 0 by this equation over here is c times x of 0 plus d times u of 0. But the initial condition is that x of 0 is equal to 0. So this is equal to simply d times u of 0. So we'll keep that in mind. And since u of 0 for the delta input is equal to 1, then let's just write this as d times delta of 0, and that is simply equal to d. Right? Now let's take a look at x1, and we'll derive y1 from that later. x1 equals a times x0 plus b times u0, and that is equal to, we have simply that actually. Well, not quite simply that, because u0 we can simplify, so that is a times 0, x0 is 0, plus b times 1, that is simply equal to b. Now let's try x2, that's equal to a times x1 plus b times u1, and that is equal to, we have an x1 over here, simply a times b plus b times 0. Remember, u1 is equal to 0 because it's a delta function. So this is just ab. I forgot to do y1 over here. So y1 equals c times x1, which is c times b, plus d times u1, but u1 is 0. So that is equal to simply c times b. Let's do y2 here, equals c times x2, which is c times a times b plus 0. Let's try x3, equals a times x2 plus b times u2. B times u2 is going to be 0, we know that. X2 we know is ab, so it's a squared b. And y3 will be similarly equal to c times a squared b, and so on. So in general you will get xt over here equals a to the t minus 1 times b, and yt over here is simply equal to c times that, which is c times a to the t minus 1 times b. Now recall that our expression for the impulse response, the general input output function, was from the last lecture. Y of t was equal to sigma I equals 0 to t ut ui h of t minus I. Now this is assuming one, causal, and two, u of t equals 0 for t is less than 0. And let us just check to make sure that if I give my u of I to be delta of I, then this turned out to be h of t. So if ui equals delta I, okay, because that's my input function, then only for I is equal to 0 does this does this thing make any give you a non-zero term. Y of t is equal to simply u of 0, right, which is 1 times h of t, and that is simply equal to h of t. So we have confirmed that our equation actually does give us h of t. It's just a thing on the side, not directly related to this problem, but useful enough to have established. Now what we are going to do is simply write out our expression for y of t as h of t. So we have for this system so remember when t was equal to 0, it was d, and otherwise so this is our impulse response for this system. Now let's try this on a real example. We'll take a very simple one that we had done early on, a compound interest example. If if you look back to when we were introducing state space system, you'll find that there was a compound interest example that I used to introduce the concept of discrete time systems. And that discrete time system was S of t plus 1. S is the total accumulated money in your bank, and t is the month number, equals 1 plus the yearly interest rate divided by 12 times st plus u of t representing the amount of money you put in each month. And our output y of t was simply equal to the total money accumulated s of t. So here, if you just compare it with the above example that we just did, we have a is equal to 1 plus r over 12, b equals 1, c equals 1, and d equals 0. So we get an impulse response h of t equals 0, t is equal to 0 because that's d, and the other ones are c, which is 1, and a 1 plus r over 12 to the power of t minus 1 times b. So it's simply this. Let's try to graph this impulse response. And so this is t going this way, starting from 0, 1, 2, etc. And as you can see, the initial point is actually 0, and then you have 1 plus r over 12 to the power of t minus 1 which is basically equal to let me see, is equal to just 1 over here, and then it is equal to a little bit more than that, 1 plus r over 12 to the power of 1, okay, which is slightly more than 1. Let's say it's over here, okay, and then it keeps on going up. So you can see, because the rate of interest r is a positive number, 1 plus r over 12 is slightly more than 1, and so it will increase as t keeps increasing. So what we see over here is that the system is unstable. Because with a single input of delta of t, which is by no means unbounded, it is very bounded, it's just got a 1 at time t equals 0 and 0 everywhere else, you're getting an output, the impulse response, which is keeping on growing unbounded till your time. So that is the hallmark of an unstable system. But in this case, if what you're getting out of it, here we have, this is y of t, what you're getting out of it is money, you usually don't mind the money increasing unboundedly. So that's the situation. So now there is one thing I'd like you to think about, and I think this will also be covered in the discussions, is given only h of t, for some linear time invariant system, can you determine if the system is Bibo stable or not? So this is left for you to figure out with the help of a discussion, or preferably actually on your own without the help of a discussion. Okay, next what I'm going to do is I'm going to show you how to do convolution graphically. So as we know, as I was saying, as we know, y of t, the output of a linear time invariant system, is the input u of t convolved with h of t, and this, in the simplest case, is sigma I equals 0 to t ui h t minus I, as we have just seen. And this is assuming two things: one, causal, two, u of t equals 0 for t less than 0, right? So we'll stick with that case for simplicity. Let me try to illustrate this thing here for you graphically. So this is of course the input u of t or u of I, and this is some munging of the impulse response h of t. We actually have h of t minus I. Well, what does it look like graphically? That's what we want to take a look at right now. So I have some things already prepared over here. Take u of t, paste it, and we find, okay, so I'm just going to take an example with just a few values of u of t. Wherever it's not shown, we'll just assume it to be 0. So u of 0 is equal to 1, u of 1 is equal to 2, u of 2 is equal to 3, a simple enough example. And then we'll take an h of t to look like this. So h of 0 is equal to 2, then it becomes 3, 2, 1, 0, and then forever after it is 0. So how do we, suppose I want to find y0, y1, y2, y3, etc. How do I go about it? So I'll start with y3, just I'll take t equals 3. Just for fun, I'll start with t equals 3, then we'll do the others. And then we get, so y3 equals what? Sigma I equals 0 to 3 ui h of 3 minus I. That's what it's going to be. So ui is simple enough. If I just replace t by I over here, that's ui. So let me just do that. I'll just copy this and put it here. I'll just make this ui instead of, let me make it ui like this. Sorry, this is I, like this, and this is ui. Now I want to find h of 3 minus I. So before I find h of 3 minus I, let me copy this and then just put this here. This is still just h of t. I'll, just like I did for the other one, I'll make this index I and I'll write h of I over here. And then I want to find h of minus I first. So this is ui here. Ui, so hi. Now I want to do h minus I. What does h minus I look like? So if I take, let me just copy this over and stretch it a little bit, get rid of this and move all of these out. Move that back. And in fact, I'll stretch it onto the other side. So this is going to be I now, again, but I'm going to be plotting h of minus I. So minus 1, minus 2, minus 3, minus 4, like this. So if so now we can see that if I take I to be 1, then minus I, if I take I to be 0, then minus I is also 0, and h of 0 was this, so I can just pull this over and put it right over here. That was h of 0, no problem there. If I take I equals 1, then minus I is minus 1. What was h of minus 1? H of minus 1 was 0, so this is 0. Similarly, h of minus 2 is 0, and so on. So these are all 0. How about minus 1? Then it becomes h of minus 1 is h of 1. So you get this. So basically what you get is a mirror image of the thing around the vertical axis, just like this. This is h of minus 2. This is now, this here is at minus 3, and at 4 it's 0. So it's a mirror image, right? And in fact, what I'm going to do is I'll simply wipe out these because I don't even need them anymore. And that's that. Okay. This one should probably also be I like this. So what we've got is h of minus I, but not h of 3 minus I. What is h of 3 minus I? H of 3 minus I. If you think about it for 1 second, then h of 3 minus I is simply shifting this whole thing right by 3. So let's do that. As it happens, I should not have wiped out all those numbers, so I will run them all over again. Okay, so 0, 1, 2, 3, 4, like this. So if I shift it by 3, so that's 1, 2, 3. Let me just draw a quick line out there for the shift. Maybe I'll draw it in a different color. This is going to be equal to t, which is 3 in this case. So if I do the whole lot, then that's 1, 2, 3. Let me do that again. Trying not to grab the thing at the bottom. Right, 1, 2, 3, and here we have it. This is h of 3 minus I, right? Now, so finally we've got this here. We've also got ui from before. So all we have to do is take each one on top, take each item and multiply it by the corresponding item. The easiest way is to just put the two figures one on top of the other, and then do the multiplication and add them up. And that's what we'll do. So this is h of 3 minus I right here. That's in red. And the part in blue is here. That's ui. So yes, ui is over here. Let's get the alignment a little right. Well, okay, so I'll stagger them a little bit so that you can see them apart. And because they happen to have exactly the same values, right? So now we can just multiply the two together. So now we have y of 3 equals 1 times 1, 1 plus 2 times 2 plus 3 times 3, and there's a 2 over here, but u of t is 0, so there's nothing else. So this is 14. So that's how you get y3 equals 14. Right. So to get a single value of y, you have to do all this work. But that's the nature of convolution. Okay, now let's try y1. That will be equal to sigma I equals 0 to 1 just actually. ui h of 1 minus, so that should be a 1 minus I. Now because we have all these previous things already available, that's right there. Okay, wipe out these things over here, and we have h of minus I, which will bring copy and bring down, and now we want h of 1 minus I, so we just shift h of minus I by 1 to the right. So alright, let's take this, copy that. Now we take this gap here to be 1, t equals 1. Get my t equals 1 like this, and I just make a straight line out there. This point here is 1, and I need to shift this, all of this, by 1, so you get this. Oh, okay, something like that. The 2 actually goes there. And this is h of 1 minus I, where this here is I. So if I put the two together on top of each other, get rid of a few things here. I should have kept the 0 location around because it to match the 0 location. So okay. So now what are the products? The products are, so 0 and 1 and 2, these three red things are multiplying 0. There's nothing blue there. So y1 becomes equal to 1 times 3, which is 3, plus 2 times 2, which is 4, and y1 is equal to 7. Similarly, if you do the same thing all over again for y2, y0, etc., you will get y0 equals, where is y0? It's 2. y1 we already know is 7. y2, if you do that, then you will get 14. y3 we have just done, and that is also 14. y4 will be 8. y5 will be 3. And y6 will be 0 and above, so y7, y8 and so on. Above will be equal to 0. So let me see if I have a plot of this somewhere. No, so I'll just plot it. And so what was it now? y0 was equal to 2 right there, y1 was equal to 7, it will be in the middle here, y2 was 14 right here, y3 was also 14 right there, y4 was 8, which is here, y5 was 3, which is here. And I can draw the vertical bars. And the rest of them over here are 0. So this is basically what you have to do for convolution if you work things out by hand laboriously, which is pretty much the only way to do it, unless you do it by computer, or unless you do it by some fancier means that we probably won't have the time to get to in this class. So that was the illustration of convolution. So finally, let me tell you a little bit about continuous time systems. So far we've been doing everything with discrete time systems, but now we have a continuous time linear time invariant system. So the input is u of t, the output is y of t. So everything we have done for discrete time systems can be done with continuous time systems. Let me outline the flow for you. So remember that in the discrete time system case, we applied the delta function, the discrete time delta function, which was just a 1 at t equals 0 and a 0 everywhere else. So in the continuous time case, you have to apply something called the Dirac delta function. Dirac delta function, which is a very weird function. It basically has the property, it's written like this, delta of t, and that is equal to infinity at time exactly equal to 0 and 0 everywhere else. So this is not really a function because function shouldn't take values of infinity, but people still treat it like a function. And its great operative property is that the integral of this function delta of t, so delta of tau d tau is equal to 1 for any epsilon greater than 0. So the limits are between minus epsilon and plus epsilon. So you take a small region for the integration that includes 0, and if it does, then the integral of the delta function is equal to 1. And if it doesn't include 0, then it's not 1, because the value of delta of t is 0 everywhere outside 0. So it's a funny kind of function. You may have encountered it in physics before. And then what you do is you apply delta of t as input to the system, record y of t. This is the impulse response, is the impulse response h of t. And a very similar convolution relationship in the continuous time domain also holds over here. Once you have h of t, you know everything about the continuous time system. So given any u of t, if u of t through this linear time invariant system gives you y of t, then y of t can be written using that impulse response as integral from minus infinity to infinity of the input u of tau times h of t minus tau d tau. See how similar this is to the summation expression or the convolution expression in the discrete time case. This is the continuous time convolution, and you write it in a similar way, ut star ht. This is now continuous. So the proof is very similar to the discrete time case, except that you have to decompose this u of t in some kind of integral using delta functions. By the way, causality over here for continuous time systems is exactly the same essentially as for discrete time systems. LTI CT system is causal. H of t is equal to 0 for all t less than 0. It's as simple as that, right? So, and if the system is causal, then the convolution expression above simplifies a little bit. It becomes y of t equals, so you see that for any tau greater than t, this h of t is going to be 0 if it's causal. So it's simply integral minus infinity to t u of tau h of t minus tau d tau. And that's all I really wanted to say about continuous time systems in the context of linear time invariance. So that's it for the linear time invariance part of the class. Next we will look into a signal processing thing called the discrete Fourier transform, or DFT, in class.